to the next session of Introduction to Biomedical Optics from Theory to Application. In this session, we will learn about various ways how the light interacts with the tissue. The light that you can, for example, you can start the light from your mobile phone, the torch in your light on your mobile phone, and then you can just point it to your fingers, and then you can see what kind of phenomena that occur over there. So you can see that it is the white light is coming out from the torch, but when you introduce to your finger, it actually becomes red in color, right? So there are a lot of phenomena that actually occurs once you introduce the torch in front of your fingers, right? So let us see that one by one. We will try to slowly develop that all the phenomena that actually occur. So the first thing that occur in a light tissue interaction is the reflection, right? So you can assume that you have the light source over here, and it's shining the light. As of now, it's just a simple light source. Could be a torch, for example, and the green color is it's just showing that it is a particular wavelength. Okay, so what I am trying to do is I'm shining a monochromatic light source which is in green in color, right? So having a peak wavelength of around 545 nanometers. Now it interacts with my tissue, and it actually gets reflected at a particular angle. So reflection is the first thing that it could occur. That's the first thing that occurs on the interface of your tissue. The light interacts with the tissue, and then it just reflects back. So that is the first thing that can occur. Let us see what has happened in the next phenomena, right? So another thing that can happen is the refraction, right? So refraction means the light is going to enter, and then it is going to bend, and it's going to travel in a same path, and then once it comes out of the tissue to the air, then it will again bend, right? So you might be knowing about the Snell's law, right? N1 sin theta I is equal to N2 sin theta I, right? So this is based on the Snell's law. So how much is the bend is based on the refractive index of the tissue and the air. However, seldom do we see that the refractive index of a tissue is kind of a homogeneous, right? So it's, for example, you see your fingers, so it will not be having a same refractive index throughout the whole finger, right? It will actually vary based upon the various tissue constituents does the light interact with it, right? So it's a heterogeneous medium. So we seldom see this refraction. We see a lot of reflection definitely, but we seldom see such kind of refraction. Refraction event occurs more or less when we have a dielectric slab, for example, a glass slide, right, or a kind of a glass jar, right. So if you shine the laser on the glass jar, you will see that it will actually bend, and if there is a water inside that glass jar, it will bend it further, and then once it comes out of the glass jar, it will again bend in its original direction, right. So there are a lot of refraction happening when you assume that the refractive index of that particular media is homogeneous throughout the the domain where it is propagating, the light is propagating. So let us see what happens other than reflection and refraction. So as you can see over here, the light is going to enter, and then it scatters. There are different kinds of scattering. The one which is occurs and the photon, that the green ball that you see is nothing but the photon. We are assuming the light as a particle, and it reflects with the many tissue constituents like collagen, protein, hemoglobin, and it moves forward with the scattering. It's like a game of ping pong. If you have seen that you just hit many not ping pong, it's a pinball, if you have seen that game. So it has many obstructions, right. So you hit that ball, and it touches the one of the obstruction, but it still moves forward, right. So if it is moving forward with the hitting of many obstructions, it is known as forward scattering, right. And some of the photons will actually get absorbed. What do you mean by absorbed is that a photon has its particular intensity. For example, a photon has we cannot tell it what power it might be having, but if you say that if the complete light source that you say it's around 100 milliwatts you're shining, it may happen so that it may completely gets absorbed within the tissue itself before it actually comes out, right. So that is the absorption. It will slowly decay inside the tissue before it actually comes out. Okay. So this phenomena is involving both the scattering as well as the absorption. Now it could happen so that in addition to the forward scattering there could be also backward scattering. That is again if you have seen the pinball game, the ball hits the obstruction and then it can move backward as well, right. So so if there is a backward scattering along with the forward scattering, then the photon that you shine, as you can see over here, it's coming from the air medium, it interacts with the tissue, you have the forward scattering, and then instead of getting absorbed, it is getting backward scattered. So it's a game of probability. So it's only based on the probability you can see that forward scattering and backward scattering will occur together. But in a whole sense you will see that everything would be in a kind of a probabilitical statistical manner. This thing will happen, right. So now so once you see the both forward and backward scattering, the backward scattered light can be actually detected using a light detector, right. So it could be any detector, for example silicon photodiode, it could be avalanche diode, or it could be photomultiplier tube, right. Now if you are detecting the light which is getting backward scattered, then it is known as a diffuse reflectance measurement. What happens in this is why it is known as diffused, because the light has gone under a multiple scattering events, right. So the light which goes inside the tissue undergoing multiple scattering event, it actually becomes diffused in nature, right. So and that's why along with this you also have reflection. So it has reflected backward, right. So it is known as diffuse reflectance measurement. One of the example you can see is an example from Applegate et al. Paper in Biomedical Optics, Journal of Biomedical Optics 2020. What he has shown is that you shine the light on your hand and then you have a camera in front of it. So the light propagates through your tissue and then it diffuses inside this tissue. It has a lot of blood vessels as well, right. So if you shine a green light, you know that green light gets absorbed significantly by the hemoglobin, which is the main constituent of the blood, right. So you will see that the green light which is being shine on your tissue will be absorbed more by the blood vessels. So if you have a camera in front of it, you will say that the blood vessels will be dark in color, right, because those green light is being absorbed, right. So you can see over here the blood vessels are this one, and it's actually dark in color, right. So the only challenge that we have is that this is a kind of a banana in shape, right. So if you see this, so you can see that the light is coming and it will go backward, and it would be not just over here, that is backward in nature, it will also go in the upward direction, again reflected, back reflected, okay. So this happens on all the sides, isotropically on all the sides, just it happens so that I am showing it in the bottom, but it happens also in the top. So you can also have a detector in the top, and you can also measure the diffuse reflectance. Okay. The biggest challenge that we have over here is that as the light propagates further inside the tissue, the intensity of the light that comes out actually significantly reduces. Okay. So that is the biggest challenge that we face. So you can only characterize the properties of the tissue which are superficial, that is only on the surface of the tissue, for example blood vessels that are kind of on the surface of the tissue, but you cannot have a very deep tissue investigation of with such kind of diffuse reflectance measurements, right. So that is the biggest challenge that is with this diffuse reflectance measurements. You can probe at approximately from 2 to 3 mm depth through this from the surface of your tissues. And of course on the surface, on the top, if there are some kind of skin melanoma or any lesions are there, those things you can visualize as well. Okay, so we talked about reflection, refraction, we talked about absorption, and now we talk about backward scattering leading to your diffuse reflectance. So let us see what else could actually happen. So now it could also be the case that the forward scattering is dominant, right. So the light which is hitting many of the obstructions within the tissue, it somehow propagates through the tissue and comes out. Okay, and you can see that there is significant scattering. So this is just one of the path that I have discussed. It could go from a multiple paths, and this is a path of a single photon that I have discussed as of now, right. So it passes through the whole tissue and then comes out. Now the same detector can also be used on the other side of the tissue. Now as you can see, now again there are a lot of scattering events that are occurring, and the photon that now we talk about is now diffused in nature, because there are a lot of scattering that occurs before it actually comes out of the tissue. That is why the name diffuse. Now instead of reflectance, we will put it as transmittance. So diffuse transmittance is what you can say once it actually propagates through the tissue to the other side of the tissue. One of the example is of this kind of measurement is given by Professor Taroni, in which she has used such kind of measurement on a breast. So they have the source and the detectors, and they try to propagate the light through the breast. After compressing the breast, they kind of propagate it through the breast, and then from there you try to understand where there is more absorption of various tissue constituents such as hemoglobin. Hemoglobin has two sub constituents such as oxygenated hemoglobin as well as deoxygenated hemoglobin. You have collagen, you have lipid, you have a lot of different kinds of proteins, you have water, fats, a lot of things, tissue constituents are available. So all of them can be actually quantified if you shine the light, once you compress the breast and then shine the light from one side and detect the light from the other side, right. So this is a transmittance type of a measurement. The light has to propagate through the tissue, right. So this technique is known as diffuse reflectance. Now there could be another technique as well, where the light is actually either it could be reflected as well as transmitted. So over here I am just showing as a transmitted, but the case could also be that it is being reflected as well. Now what is happening is that you can see this green photon which is interacting with the tissue. It occurs through multiple scattering, and then it interacts with a fluoropore. Now a fluoropore is a molecule which could be both endogenous as well as exogenous. Endogenous means the fluoropore is a part of our own human body. Exogenous means that it could be intravenously given or given to you for the measurement of a particular disease. Okay. So what happens is that what is the purpose of this fluoropore? If I shine the light which is green in color to this fluoropore, what will happen is that it will absorb certain intensity of light of this green color, and it will re-emit on a different wavelength. It will kind of always be higher wavelength because lower energy. So if you shine the green light, it will give you red light, for example, or it can give you a NIR light, for example, near infrared light, for example. Okay, here you can see that for example, we have taken it as a red color. We shine a green color and we get a red color. Now again, the biggest challenge with the fluoropore is that the light that is emitted by the fluoropore is that the intensity of the light is significantly smaller. Maybe it's in order of less than 10 power 4 to 10 power 6, right. So there is significant reduction in the intensity of the light emitted by the fluoropore. So before it actually comes out of the tissue, it has to again go through lot of scattering, right. So once it goes through the lot of scattering, again you can see that it will the intensity will reduce significantly, right. So you need a very specialized detectors along with filters to remove the original light source to detect this light which is emitted by the fluoropores. This technique is known as a fluorescence technique, and then this is an example of the fluorescence probe which is attached to the dendrites over here, right. Similar to the fluoropore, so in fluoropore it is more or less endogenous chemicals, or it could be an exogenous chemicals. Similar to this, there is one more technique which actually targets the molecular interaction of the light, right. So there are many molecular interactions. For example, you have vibrational spectroscopy, you have infrared spectroscopy. So there are a lot of as you have already discussed in the last class of spectroscopy. So you shine a green light, and then a particular molecule, for example it could be a water molecule, right. If it the band energy band of that particular light source is equal to the excitation of the molecule, so it actually start to vibrate, right. So that is the basics of the vibrational spectroscopy. It will start to vibrate, right. Now because of this vibration, it could also emit a particular wavelength, right. So if you shine a green light, then after the interaction with the molecules, it will not only give the green light, but it will give a light which is slightly shifted toward the right and left of the green light. For example, we shine the light of green, that is 545 nanometers. It will not just give out the 545 nanometers, but it will give you something of 555 nanometers, 560 nanometers. So there would be a significant peaks, and these peaks actually correspond is a kind of a signature for many different molecules, right. So each molecule will have its own signature of these peaks. Like for example, paracetamol will be having its own peaks. There is another lipid, it would be having its own peak. We talk about calcium, it could be having its own peak, right. So based on a specific molecule, we are moving from one molecule to another molecule, different molecule, the peaks actually will actually vary. So again, the light which is developed or it is is generated by such kind of molecular interaction is kind of very less, right. So and again it has to go through multiple scattering before it comes out of the tissue, right. So here you can see that I shine a green light, and after the interaction, molecular interaction with the with this molecule which has been brown in color, it emits a kind of a shifted light source which is in yellow in color, which I am representing over here, and then it again undergoes multiple scattering before it can detect over here. So this scattered, this shifted, wavelength shifted light source detected is known as Raman scattering. And again, the biggest challenge more than that of the fluorescence is that its intensity is even lower as compared to the fluorescence. So in Raman it could be going as less as around 10 power 6 to 10 power 7 to 8 order of magnitude lower than the light intensity that you apply, right. So that is a challenge that you actually face if you do Raman spectroscopy, right. So here you can see that this kind of peaks you will actually get, and these peaks are a signature of a particular molecule, and so when you talk about tissue, there are so many molecules, right, and then there are so many peaks overlapping with each other. So when you do for such kind of tissue, it becomes you need to have for example very thin slice of tissue, or you need to apply the light focus in a very small area of the tissue. So you try to target very specific regions. For example, it could be a cancerous region, breast cancerous region, where the and if it is an invasive ductal carcinoma, then there will be a lot of specific type of calcium type 2 calcium would be more in those invasive ductal carcinoma regions, which is kind of where it is calcified, right. So, so you try to focus significantly on those small regions, then you can try to remove the other the peaks and try to focus the peaks of the type 2 calcium, right. So, so those are the challenges when you face when you actually talk about Raman spectroscopy. So, now let us summarize what we learned today. So, you can see that you shine the light from the light source, it could be through light emitting diode or it could be using the laser. It will, one of the thing that it could happen is that it could reflect, right. Next, which it could seldom happen with such kind of tissues, human tissues, is the refraction, right. It is only for a homogeneous media, but in our case we seldom see any of our tissue which is kind of homogeneous, everything is heterogeneous. Okay, the light that is going through the tissue might get also absorbed, right. So, it can completely get absorbed. For example, you shine the red light, you can see that it's your complete finger is becoming red, right. Sorry, if you shine the white light, your complete finger becomes red. Now, but if you shine blue light, you can see that nothing, the blue light will absorb very quickly in your tissue, right. So, absorption is very high for blue as well as green light. Okay. Now, other than the absorption, you could also be having the backscattering along with the forward scattering, and the backscattered light can be detected using diffuse reflectance measurement. The light could also be having significant forward scattering along with the back scattering. So, everything would be there, forward scattering and back scattering both would be there. Now, if forward scattering is going to be more, that could be based on the properties of the tissue, that is scattering coefficient is lower, for example. It could propagate through the tissue completely and then come out, right, and that measurement would be diffuse transmittance measurement instead of diffuse reflectance measurement. Now, there could be many interactions. It could be a fluoropore that we have that we discussed some time back. It could be endogenous or exogenous. Now, based on that, it could be if I shine a green light, I can get a significantly shifted red light, for example, right. So, that is fluorescence. And then we talk about molecular interaction, where we shine a green light, but we get a very small shift in delta, right. So, that small shift in delta would be the Raman scattered light. So, that is coming from tissue, and from there I can see a particular signatures, try to focus on a few of the signatures which are kind of cancer biomarkers, and then I try to diagnose whether it is normal or cancer, right. So, that is what happens when you when you just shine light to your tissue. There are a lot of interaction that happens, and this slide actually summarize all the different kinds of interaction that occurs within the tissue. Okay. Thank you.